Have you ever wondered about black holes? These enigmatic regions of space have fascinated scientists and stargazers alike for decades. Those mysterious objects in space where gravity is incredibly strong, so strong in fact that they can pull in everything around them, including stars and planets. They're so powerful that not even light can escape them. This is why black holes appear completely dark, as they trap all light within their grasp. But did you know that black holes also have a strange effect on time? Near a black hole, time behaves in ways that are completely counterintuitive to our everyday experiences. Imagine a place where time slows to a crawl, a place where the closer you get to the black hole, the slower time moves, where minutes feel like hours and hours feel like years. This isn't science fiction, it's a real phenomenon observed by scientists. That's what it's like near a black hole. The event horizon, the boundary beyond which nothing can escape, marks the point where time itself seems to stand still. This phenomenon, known as time dilation, is one of the most mind-bending predictions of Einstein's theory of relativity. It challenges our very understanding of time and space. In this essay, we'll embark on a journey to understand why time slows down near a black hole. We'll explore the science behind these cosmic giants and their incredible effects on the universe. We'll delve into the mind of Albert Einstein and explore his revolutionary theory of relativity. His insights have forever changed the way we perceive the cosmos, and we'll discover that time, once thought to be constant and unchanging, is actually relative and dependent on gravity. The stronger the gravitational field, the slower time moves. Get ready to have your mind blown. The universe is full of wonders, and black holes are among the most fascinating of them all. Join us as we unravel their mysteries. For centuries, we believed that time was constant. 1 second on Earth was 1 second everywhere else in the universe. It was simple, intuitive, and, as it turns out, wrong. Albert Einstein, arguably the most brilliant physicist of all time, revolutionized our understanding of time. He proposed that time was not absolute but relative. It could be stretched and squeezed, sped up or slowed down, all depending on how fast you're moving or how strong the gravitational pull is around you. This concept, known as time dilation, comes in two flavors: time dilation due to motion, which is special relativity, and time dilation due to gravity, which is general relativity. We'll focus on the latter, which plays a crucial role in the strange case of black holes. Einstein's theory of general relativity, published in 1915, is one of the cornerstones of modern physics. It describes gravity not as a force but as a curvature of space-time, a four-dimensional fabric woven from space and time. Imagine a bowling ball placed on a trampoline. The ball creates a dip in the fabric, causing nearby objects to roll towards it. Similarly, massive objects like stars and planets warp the fabric of space-time, creating what we perceive as gravity. The stronger the gravity, the greater the curvature of space-time, and the greater the curvature, the slower time flows. This is the essence of gravitational time dilation. Black holes are the ultimate cosmic crushers. They're regions of space-time where gravity is so intense that nothing, not even light, can escape their clutches. This extreme gravity is a result of a massive star collapsing under its own weight, squeezing all its matter into an incredibly small space. Imagine the Earth compressed into the size of a marble. That's the kind of density we're talking about. Now imagine this incredibly dense object warping space-time like a bowling ball on steroids. That's what a black hole does. It creates a gravitational well so deep that time itself slows down as you get closer. Space-time, the fabric of the cosmos. To understand how black holes affect time, we need to grasp the concept of space-time. Picture, if you will, a giant flexible sheet. This sheet represents space-time, the fabric of our universe. Now imagine placing a heavy ball on the sheet. The ball represents a massive object, like a star or a planet. The weight of the ball causes the sheet to sag, creating a dip. This dip is what we experience as gravity. The closer you are to the ball, the steeper the slope and the stronger the gravitational pull. This is why objects fall towards the Earth. They're simply following the curvature of space-time created by our planet's mass. Falling into a black hole, the thought experiment. Let's conduct a thought experiment. Imagine the vastness of space, the mysteries it holds, and the phenomena that challenge our understanding of physics. Imagine you have two identical clocks, one on Earth and one on a spaceship hovering just outside the event horizon of a black hole. These clocks are synchronized perfectly. The event horizon is the point of no return, beyond which nothing can escape the black hole's gravitational pull. It's a boundary that marks the limits of our observable universe. As you observe from Earth, you'd notice something peculiar. The clock on the spaceship, which was once in sync with the one on Earth, now behaves differently. The clock on the spaceship appears to tick slower than the one on Earth. This phenomenon is a direct consequence of the intense gravitational field near the black hole. This is because the spaceship is experiencing a much stronger gravitational pull than Earth, which slows down time. This effect is known as gravitational time dilation. Now imagine the spaceship starts falling towards the black hole. The closer it gets, the more pronounced the effects of gravitational time dilation become. As it gets closer, the gravitational pull becomes even stronger, and the clock on board appears to slow down even more. To an observer on Earth, it would seem as if the spaceship is moving in slow motion. From your perspective on Earth, it would seem as if time itself is coming to a standstill as the spaceship approaches the event horizon. This thought experiment illustrates the mind-bending nature of black holes and the extreme effects of gravity on time. Proof in the pudding, evidence for time dilation. Einstein's theory of general relativity has been rigorously tested and confirmed by numerous experiments. One of the most compelling pieces of evidence comes from atomic clocks, the most accurate timekeeping devices ever created. In the 1970s, scientists flew atomic clocks on airplanes around the world. When they compared the clocks to those on the ground, they found that the airborne clocks had ticked slightly slower, just as Einstein's theory predicted. This experiment, known as the Huffel-Keating experiment, provided direct evidence that time is indeed relative and affected by gravity. The stronger the gravitational field, the slower time flows. GPS and time, the practical application. Believe it or not, we experience the effects of time dilation every day thanks to the Global Positioning System, or GPS. GPS satellites orbiting Earth rely on atomic clocks to provide precise location data. However, these satellites are situated in a weaker gravitational field than clocks on Earth's surface. This means that time flows slightly faster for the GPS satellites than it does for us. To compensate for this discrepancy, GPS satellites have to adjust their internal clocks to ensure accurate positioning. Without this correction, our GPS systems would be off by several miles each day, making them practically useless. The future of time travel. The concept of time dilation raises a tantalizing question. Is time travel possible? Time dilation, a phenomenon predicted by Einstein's theory of relativity, suggests that time can be stretched or compressed depending on the speed at which an object is moving or the strength of the gravitational field it is in. While we haven't quite figured out how to build a time machine, the laws of physics don't necessarily forbid it. Theoretical physicists have proposed various models such as wormholes or cosmic strings that could potentially allow for time travel. These ideas, though speculative, are grounded in the mathematics of general relativity. If we could somehow harness the extreme gravity of a black hole or travel at speeds close to the speed of light, we might be able to distort time significantly enough to journey into the future. Imagine a spaceship traveling at near light speed. Time for the passengers would slow down relative to those on Earth, allowing them to leap forward in time. However, traveling back in time is a much trickier proposition, fraught with paradoxes and logical inconsistencies. The famous grandfather paradox questions what would happen if you traveled back in time and prevented your grandparents from meeting. Would you cease to exist? These paradoxes make backward time travel a subject of intense debate and skepticism. For now, time travel remains the realm of science fiction. Movies and books have long explored the possibilities and consequences of time travel, capturing our imagination and inspiring future generations of scientists and dreamers. But who knows what the future holds? As our understanding of the universe deepens, what once seemed impossible might become achievable. The boundaries of science are constantly being pushed, and today's fiction could be tomorrow's reality. Perhaps one day, armed with a deeper understanding of the universe and its mysteries, we'll unlock the secrets of time and embark on adventures through the annals of history or voyages to distant futures. The quest for time travel is not just about moving through time. It's about expanding our horizons and exploring the very fabric of reality itself.